of the TCP/IP, right, protocol. So overlay on top of the internet. P2P, it is a P2P network of computer nodes. And then P2P nodes share a blockchain. How do they share? Through APIs, right? ChatGPT is also APIs, right? So blockchain and artificial intelligence both are using APIs, list of APIs. They have the computers talk to with each other with a different objective. So in the case of blockchain, what is the objective? Let's keep the ledger safe, right? Let's maintain the ledger. Let's build the ledger together. Okay, inside this ledger, let's put the transactions, right? And then verify these transactions and put them into the block. Okay, then we can even create a currency system, right? What is the case of AlphaGo? How many computers AlphaGo has used? Thousands of computers, right? And how do they utilize cloud of computers? To win the game of Go, right? In order to win the game of Go, what do you need to do? You need to investigate large number of options that you can place, rock, right, on the board, right? How many options do you have? Lots of options. So you have to do a breadth search, in a given condition, in a given state, you have to investigate many different options that you can place your rock, right? White rock or black rock, right? And then what do you need? Do you just need a breadth search? No. If you place your rock in this position, what is your chance of winning the game at the end, right? Then in order to investigate that, what do you need to do? You need to go down the tree, right, into the depth, right? Maybe 10 depth. After 10 plays are made, what is the chance of winning the game? So you have to do breadth search and the depth search as well. And then in order to do the breadth search, how many options do you have? Thousands of options. So you have given this job, you go down the list, go down the tree, 10 depths, and then figure out what is the probability of winning the game. And then each and every, placement, you can investigate, you can have the computer to compute the probability of winning the game. Then you have 10,000 options of, placing a rock, and then winning probabilities, right? That's how, they, designed the AlphaGo, right? That's the basic principle, right? Breadth search and depth search for each and every options. Obviously, computer can do better than humans, right? Because they are utilizing cloud of computers, right? But if we limit the power of, if we limit the energy spent for single placement of rock, let's suppose, then who will win? Humans or cloud computer? Humans still win, right? We only burn like 1 watt of power each second, but the computers burns like thousands of watts, right? Using these GPU servers in the cloud. So if we consider the amount of energy for computation, still the humans have the advantage. Anyway, so we are using computer network. In the case of blockchain, we use them to make ledger, right? And then in the case of artificial intelligence, we are using the computer networks to optimize or to make decisions like that. Okay, so this is a little bit different purpose, and then both of them work through application programming interface. That's the actual artificial intelligence. If you have many APIs, accumulated, then you can have these APIs work together, just like an agent. And then we could build a multi-agent system. Right? So here in this case, blockchain is trying to maintain this ledger. So basically a block here, that's the language they use, but actually this is a file, right? A computer file. In this computer file, the size of this computer file is about 1 megabyte. And then inside this computer file, there are transactions, okay, about thousands of them. And then you connect these computer files through secure hash function from one to the next, and so on and so on. So every file is connected. Right? We call it blockchain. File is a blockchain. And then we sometimes use this blockchain as, to imply the technology itself. Okay. So blockchain is to mean a digital ledger. Blockchain is a chain of blocks, but actually it is a chain of files. Each block is time stamped. There is a time for each block. Each block stores transactions. Blockchain also implies the technology itself. Okay, so as time goes on, more blocks are connected to this chain of blocks. Okay, blockchain is left open for viewing, right? So open blockchain. Any new node can join. Miners are everywhere. It's desired to be, and consensus mechanism plays the key role in blockchain. So which block contains the canonical transactions, and then which blockchain has stored more energy into it. So how much energy is burnt to create a blockchain, right? More energy is stored in the blockchain, then it is more difficult to hack it, right? More difficult to break it, okay? In order to break it with some false information, you have to redo all the work. So you have to spend the same amount of energy, right? So the longer the blockchain, the longer the energy stored in it. Okay, so that's the mechanism. And I have used a language called storing of energy. So what has been transformed? Somebody a network, blockchain, Bitcoin network spend large amount of electric energy to create each block, right? And then there is what is the output in terms of storage? Energy spent, what came out of this effort? Each block there is a Bitcoin, new Bitcoin created. So energy spent has been transformed into what? Bitcoin. Okay. So that's so you can think of this Bitcoin as a storage of energy. Okay. And then you can use this energy, give this energy to somebody else. Then you can ask for their time and energy spent for me. Right? So basically that's what we call services, assets, and so on. Okay. So this is the structure of a block. So if we take a deeper look inside the block, there are two parts. First, block header. Second, block body. Block body has thousands of transactions, and then we do something called a Merkle tree. And then there is output, which is a Merkle root hash. Okay, so this is a hash value, and the timestamp and hash of the previous block, like that. So these are the critical ones, and then you have a version number, and then nonce, and all the others. Bitcoin has about exactly eight fields stored here in the block header. We'll get to the details later on, right? But as far as concerning this lecture, these three are the critical ones: hash of previous block, and then timestamp. Okay, and then hash of the block body. Okay, so if you change something in the block body, that means some transaction has been altered accidentally or with purpose, both, right? If something changes, then hash value changes, and then it will create a chain reaction. Everything will change after that. So anyone can detect right away, something has happened. Maybe this blockchain is no good, and I can throw it away. Okay? I'm not going to use it. Okay? I'm not going to spend more energy to extend it, right? Because something went wrong. This blockchain is no good. I'm not going to use it. Like that. And there is a role for secure hash function, but this is well known in cryptography. Basically, hash function does the summary of a file. So basically, for a 1 megabyte file, hash output is just 256 bits, and then this 256 bit summarizes the file. Okay, you will get to know what the meaning of this summary is. Okay, this is a collision resistant hash function. So if you have a bigger space coming down to the smaller space, there must be a collision, right? But this 256 bit is large enough, you cannot find collision event in your lifetime. So basically, that's the argument for collision resistant hash function. We'll get to know this later on. So here is the very important chart. But maybe the most important chart in this course is this. So here, content in the blockchain cannot be changed easily, right? Can be changed because it's a digital file. But what do you have to do in case there is a change, right? Especially when you have an intention to deceive somebody. Okay, that's the double spending attack scenario. So what happens when any alteration is made? So what happened, alteration made in the transaction? Well, alteration made in the block header. Then something has changed because of the property of a hash function. It will create a chain reaction of changes down the line, right? So because these are the digital files, and then when you do a hash, when you put something inside a hash function and getting the output takes a split second. Right? These days, about terahashes per sec. You can get the output of a hash function, 1 trillion times in a split second, in single second. If someone gives you 1 second, then there is a hash function generator which can generate 1 trillion hash outputs in a single second. So, getting this work redone from the alteration that you made and then change the rest of the blocks, it's not a difficult job for a computer to do. Okay? So what Satoshi Nakamoto has done is putting the proof of work. Let's make this, finding the next hash, very difficult, right? In order to do this hashy job, finding the next hash takes like 3 years for a single computer to work, right? But if there are billions of computers working together to find the next hash, it will take only 10 minutes. That's the case of Bitcoin. Then here the meaning of this heavy arrow is the work of the billions of computers working together to find the next hash. So how can we find such a hash? So basically that's easy problem. So I told you that hash is 256 bit, right? Hash output is 256 bit. So hash output is a number because it is a 256 bit like this. See, the number of bits is 256. So can you write this as a number, integer? So yes, you can, because if you use binary system to represent that, then this is a number between what? This is a number between 0. So hash is a number between 0 and 2 to the power of 256 minus 1, right? So for example, if you have 3 bits, right? This is the representation 0, 1, 2, 7, right? And then 7 is what? 2 to the power of 3 minus 1, right? So same thing. If you have a 256 bit, it can be transformed into integers like this, right? This is one example. This is what humans does, and this is what computer does well, right? Computer, we give this rule, it will give you the number, right? And then you can ask now, so how do we make this proof of work very difficult? How do you do that? So this is an output that is a hash, but it is a random number, and then you can ask this random number to be this random number. Let's say hash is a number. You want hash this number to be greater than, let's say, 2 to the power of 255. You can do this, right? You can do this, right? Okay. You can let, so good hash means let good hash means this, right? This, right? $255. What is the probability of this event then? What is the probability of this event? Do you guys know? That type of things are going to what we are going to study. But can I say that this is maybe I can just let you guys try. Can you make a guess? What is this probability? Heung-No? Eh? Epsilon? Ah, very small number. Okay. Half? Okay, there is a try. All right, half. Why? All right, so this, he says, this is 256. How did you get it? Can you explain this now? So this is 1 over 2, but is this right? That's my question. So hash is one of these numbers, right? In this range, right? Now I have asked what? I need a. In the x-axis, I have 0, 1, 2, 3, 4, all the way up to where? 2 to the power of 256 minus 1, right? So this is the binary representation where bits are all ones, right? 256 ones. That is this number, right? In binary representation. Right? And then I can draw a y equals x line, right? And what I can do? Okay? And here I said that the output hash is greater than 255. So somewhere here I have a 255, right? And then I said hash is greater than that one. So I am talking about this set, right? 255, greater than that. So what is this representation here? 255. Or a bit smaller than that one. 255 minus 1, there will be. And then like this one, it will be represented as 0, 1, 1, 1, 1, all the way up to the down. So I have 255 ones, single 0 at the top, right? Right? So I am talking about this set, right? I am talking about this set versus that. So 1 bit difference, right? So single bit difference is the, so this one represents that set. So the probability of this set, I think this one has to go down. If it has to be right, I think I have to change this to this, isn't it? Isn't it? Good hash. So that means good hash here means I want my hash output to be smaller than this number, right? Then I say it is a good hash, right? Then such a probability is, because of that, is this. Now I can change the problem. I want the good hash to be this. What happens now to the probability? So this getting reduced for 4, and this is going to be square, right? Okay. Now I change this to 3, and then I'm not going to repeat this, and then you can immediately say it's 1 over 8. 4, 1 over 16. 5, 1 over 32, and so on and so on and so on, right? So that's basically, you can treat this as minus, let's say m, where m is number of zeros in front of the hash, right? So in such a case, I can define the difficulty level. I can make the I can make this very, very difficult to find the next hash because I divide the set into 2 parts. Good part, bad part. Okay? Good part, bad part. Good, well, so do you have any question? Something wrong? Any question? So this is all of a sudden, right? I jump into the probability. So I will talk about this later on. Okay. So in this part of lecture, you just understand this the meaning of a heavy arrow, proof of work. You can make it very difficult, right? So for example, if I increase the number of 0 in front of the hash, yeah.
That means that the summaries leading 0 will make the hash more difficult.
Yeah. So for example, so this is the leading number of 0, number of zeros in the hash, right? And I made the leading number of zeros like 70, right? Then how difficult this problem is? Oh, this is 70, right? So this means that good hash looks something like this. Good hash looks something like, I have zeros all the way up to 70 of them, and then there are some numbers for the rest of 256 minus 70 bits. Ones and zeros, leading zeros all have to be, leading binary bit all have to be, 70 of them have to be 0. Then the difficult in the ballpark like this. If I have to do exactly, then I have to consider this binary representation of numbers right here. It depends on exact number, right? Then it becomes exact, right? Continuous, right? And then in the ballpark, I can make the problem very difficult. Do you know how large is 2 to the power of 70 is? So that's the job of computer to do. 온라인 캘큘레이터. 혹시 캘큘레이터 있는 사람? 온라인 캘큘레이터. 2 to the power 70 어떻게 하나? 2 to the, 이거 되나? 아, 여기 있나? 이거 파워인가? 팩토리얼이지. 아, 여기 있다. So, let's see, 70. So this is 1.18 in the 1.18. So let's just 1.218, right? Times 10 to the 12, 20. 21? What 20? Yeah, 21. That's the level of difficulty. So this means what? If you find the hash, right? The probability that this hash is a good hash is this. That's the probability. Or if you want to find a good hash, on the average, you have to find this many hashes. On the average, you have to find that many hashes. 10 to the power of 21 hashes you have to produce in order to find a good hash on the average. So how long does it take for a computer to find this many hashes? huh? 크게 말해. 10 minutes? A single computer. Uh-huh. So let's suppose that the fastest hash machine in ASIC chip, right? ASIC chip is on the order of 1,000,000,000 hashes per sec. Suppose 1,000,000,000 hashes per sec. There is an ASIC chip that does hash very fast, right? And basically that's the technology. 10 to the 12 hashes per sec. Given a single second, it can produce 10 to the 12 hashes. Okay? Then how I need this many number of hashes to find the good block, good hash, right? So how long does it take? Basically, you divide this number by this hash rate. It will give you a second, right? Then what is so you divide 1.2 10 to the 21 hashes. That's the difficulty created by making 70 leading zeros as the requirement for good hash, right? And then this one, fastest technology today says hashes per second. What is so let's just ignore this part, right? Let's just, it's 1.0, right? Because it's not significant, right? So in this case, what is the result? 21 minus 12. 이거 몇이지? 9. All right. Thank you. So it is 9. That's amount of second. What is the 1 year? 1 year? 1 year. One year into second, right, is how many? 365 days. 1 day is 24 hours. Hour is 60 minutes. 1 minute is 60 seconds. So you have to multiply them. So this is again the job of the computer to do. 지우는 거 어디였어? 그러면 365 times 24 hours times 60 minute times 60 second. Okay. 31 million. 31 million. Okay. 31 million. So 1 year is about 31 times 10 to the power of 6. More than a year, right? So this is, in the ballpark, it is 10 to the power of 8, right? It's about 10 years. For a fastest ASIC machine, if you want to redo the work, redo the work for a block takes 10 years in this calculation. Given the average block generation time is 1 second. Okay. But in the case of a Bitcoin, it is 10 minutes, right? So a little bit of adjustment need to be done, okay? But you get the feeling, you know, what's the meaning of a proof of work, right? In order to do, so I can qualitatively say that in order to redo a single block with 70 leading zeros, it takes millions of computers to do, right? But if you want to do it all alone with the fastest chip, it takes years. So I can say that, right? All right. So you have to, so consensus here is that you are building this block all together, right? That's what the meaning of a consensus. If you have to do it alone, it is almost impossible because you know, this block is going to get generated, right, every block generation time. And then if you have to do it alone, in order to do this alone, you have to spend years. Another one, another years. Another one, another years, right? And so on and so on. So your block generation speed is not going to be able to catch up with the network's block generation speed, right? So you are going to fall behind. So you will not be able to change anything without your change unnoticed. So you have to do something. If you change something, you have to outpace the network's generation speed. So like you have to grow your chain faster than the network grows the chain. In such a case, you can, you can make this chain ignored, and then your chain accept it. But that doesn't happen, right? Because of this proof of work. So without this proof of work, you and others are the same, right? But because of the proof of work, the network and a single party trying to make some alteration, that their work is going to work in vain, right? It's not going to make changes, right? Without your change being noticed, right? The only way you can change is you have to have a bigger computation power than the Bitcoin network. In such a case, you can change as you wish, right? So proof of work has such a meaning, okay? So you have to work together, okay? But these days, something called the zero knowledge proof came out, and then basically this is a proof of work. Basically, your proof of work is hash output, satisfying the requirement. So if you find a good hash, you can present this found hash as a proof of your work, right? So that's the meaning of proof of work. You can prove I have worked, right? If I give this input, you get output. And then this output is good or bad, right? And then these days, zero knowledge proof came out, and they say that this proof can be done all alone by a single computer, right? And it has some applications. I will talk about that in the second half of this course. So, but for now, this proof of work is very important. Okay, do you have any questions so far for the proof of work part? Did you get a general idea, right? Why is it important? Okay. Now, suppose that somebody have a large amount of fund, right? He's Elon Musk, for example, and then try to ambush the Bitcoin. And then Elon Musk purchase large computation power from AWS, Amazon Web Service, right? cloud of computer he borrows, right, because he got a lot of money. Try to attack it. What happens? Maybe it can outpower the hash rate of the Bitcoin network. It has a bigger GPU network or ASIC chip purchased, right? Because Elon Musk has a lot of money, right? What happens? What can Elon Musk change? Let's think about that one. Because these two issues are the most important issues. Double spending problem, right? So what type of attack the person can do? In this case, that's the question. What was the double spending problem? You change something, right, in the transaction, right? And then you spend. What do you mean by spend? So basically, A is Alice, B is Bill, right? Okay, maybe Bob. Bob is a refrigerator merchant. He sells refrigerator. And then Alice is the purchaser. She's just a housewife. She wants to buy refrigerator from Amazon.com, right? And then Bob is the CEO or the merchant in the Amazon.com, right? So Alice sent 1 Bitcoin, 1 Bitcoin too much, right? 0.1 Bitcoin to Bob, right? Then Bob ships, makes sure that this transaction is published, right? And become permanent. This is not going to change, right? And then at that moment, Bob sends refrigerator to Alice, right? So that is the case for spending, right? Transaction is made. Alice sent 0.1 Bitcoin to Bob. Bob, take a look at the ledger because this is an open ledger. Actually, computer does, right? Or handphone does, right? And then this transaction has been published. So his handphone says, oh, I got 0.1 Bitcoin from Alice. Aha, since I got 0.1 Bitcoin, I'll send the merchant to Alice, right? Then spending is done, right? And then what type of attack will be good in such a case? Let's suppose that after this moment, maybe a block later, Bob sent a refrigerator to Alice, right? At this moment, right? At this moment, right? And then A is actually Alice is Elon Musk's wife, right? So he says, I want this money back, right? After she got the refrigerator, right? So he changes this transaction, Alice's address, and then another Alice's address, and then 0.1 Bitcoin. So instead of sending 0.1 Bitcoin to Bob, now she changed the transaction to pay to herself, right? To herself, right? 0.1 Bitcoin. After she got the refrigerator delivered to her, right? This is called a double spending attack, okay? And then if this alteration became permanent, what is the condition? Yeah, Alice. Can you speak a little louder?
To make it permanent, we would have to change the whole ledger.
Yeah, whole ledger.
Which would take too much
Yeah,
time. Even if it happens, like she would get more money, but the refrigerator merchant would not have any because his ledger would be false.
Whose ledger?
The Bob, the
and,
If I send money to Bob,
uh-huh.
then I will, but then I change my ledger, one of the two will be false.
So there is a question. Is there Alice ledger and Bob's ledger? So that's a good point. So basically there is two ledger momentarily, right? So one ledger, 이걸로 해야 되겠는데. There will be two ledgers, right? The legitimate ledger, right? Legitimate ledger, right? And then in this ledger, A to B, 0.1 Bitcoin, the legitimate transaction. But Elon Musk's wife, Alice, makes her own ledger, right? Change the transaction to herself, 0.1 Bitcoin. And then try to grow this ledger faster than the original ledger. So at the moment, the ledger, the public ledger is up to here, but she made more transaction very fast with a larger computation power, where Alice were able to obtain this computation power just because Elon Musk has a lot of money. Elon Musk have her utilize all of the AWS cloud computer, for example, and then build a faster ledger, like that. And then in this case, if this is published, what is going to be the choice of the rest of the network?
The longest one?
The longest one, because this has more energy into it. So they will grow this ledger rather than, I'm not going to use this because this is shorter than that. So this happens. Then this became permanent. This transaction invalidated. That's a double spending attack. Okay. So this is the only attack any attacker can make. Okay. For their own benefit. But this, as you can see, if this thing happens, what happens to the credit of the Alice? The Bob, the merchant, will not going to credit this address anymore, right? It's not going to honor this transaction. I mean the address. This address. So it will be put onto the blacklist address, something like that. And then why do you think this is the only type of attack any attacker can make? Why? So this is another very important subject. Yeah, Alice?
It doesn't change the ledger before the transaction? Like, we don't have to change the past, only create a...
We cannot change any transactions in front?
We don't have to.
You don't have to, as far as concerning this attack?
We are fastest than the...
Yeah, you have the fastest, that's the part of computation power. You need to have more computation power than the whole network has, right? That's the one thing. But what is the other part? Not only the computation power, but there is something very critical. Why the attacker can only does that type of attack? That's my question.
Because getting Bitcoin is the property, probability.
So there is it is a random event. That is also covered in this right here. Computation power, on the average, you will grow your chain faster than the network. Okay, so that's the probability part. Okay, is there any other part? So we say that these are the transactions, right? Some different address, okay? They are all open They are written in an open ledger, right? So anybody can see it. Can anybody use this Bitcoin pretending to be B? That's my question is. There is some attacker, let's say D, person D is an attacker. And then this person open up his handphone and then take a look at all the transactions. B has, let's say, B has a large sum of money, 10,000 Bitcoin. Can D pretend to be B and spend this money? Can D pretend to be B and spend 10,000 Bitcoin? Yes? No? Yes? No? Yes side or no side?
No, sir.
No. Why not?
I think because for any transaction to occur, like you need to have keys, both public and private keys.
Yeah, public and private key. Okay. So this one, there is a public key, private key system. Right? Public key, private key system. They are tied together, right? They are tied together, right? So let's say key public, key private. They have some one-to-one relation, right? And then public key is open. Anybody can see. Private key is what? You keep in your safe place. No one else should see it, right? No one else should have it except you, okay? So private key is for individual, right? Owner, right? And then public key is open. So these are actually public keys, okay? And then public key. Then who has the private key of this transaction, A to B? Who's giving the money to others? A. So this transaction is locked in, approved by person A with his private key. So we call it sign. I am approving this transaction because I am the giver, right? I am the person who's giving out this fund to B, right? Then this is given to B's public key, right? Public key. B's public key. And then A needs to sign this transaction because I am the one who's giving the money. Okay? So this transaction should be signed by A, given to some private key. And then after this has been stored inside the ledger, after it has been made public, who now owns this fund? B now has the right, cryptographic right, to spend this money. And then when this person B spends this money, what does he need to prove?
He has his private key.
Yeah, he has to prove that he has the private key for this public key, right? Right? So that's the mechanism. So what happened? B lost this public key. Lost the private key paired to the public key. Even though he thinks this is his money, he cannot spend it because he cannot prove. He cannot prove. He cannot show that he has the private key. So because when he spend this money, the transaction will be something like this form. Like I'm spending 10 Bitcoin to C. I can prove my ownership of 10 Bitcoin, and then please take a look at this transaction in the past. And then I need to sign it. Right? I have the private key for that. So this transaction becomes valid. Right? So even though there are lots of transactions in the blockchain, only the person who has the private key of the recipient can spend. Okay? So there is no other attack possible because of private key, public key pair system. Okay? So there are two things: private key, public key pair system, and computation power. So these two things make the blockchain. Okay. Any question? Yeah.
Two attackers
Uh-huh.
make same attack, then how?
크게 말해봐. 이거 잘 안 들려. 다른 사람.
그러니까 B랑 C가 둘 다 어택하면은 예를 들어서 둘 다 그 프라이빗 키를 알 수가 있잖아요. 그러면
So he's making a suggestion. In this situation, you are supposing that suppose B and C what?
B and C 그러니까 팀을 먹고 둘 다 어택하면은
So they belong to the set of attackers. Both are the attackers, and then they talk to each other.
서로 이제 프라이빗 키를 공유를 해가지고 그걸 다른 방식으로 공유를 할 수 있잖아요.
So they share their private key. They share private keys together. So you can think of these two addresses belong to a same person, right? Right? A person has two public key, private key pairs, right? That's the situation. Yeah. And then what's next? What is your question then?
B가 C한테 존재하지 않는 BTC를 보낼 수 있잖아요.
So he's saying that in such a case, B and C actually are the same person, and then B is sending to C that is not existed before. And anyone can answer him? Can such attack be made? Yes, why? No, why?
아이디가 모든 비트코인의 아이디가 모든 네트워크에 다 공유되고 있기 때문에
ID is publicized and then left open in the blockchain ledger. So what?
그래서 뭐 B랑 C가 존재하지 않는 걸 보내는 게 이제
And B and C cannot.
존재하지 않는 거를 보내는 게 모두가 이제 모든 네트워크에 공개돼 있잖아요.
공개돼. So it's a public, made public, right? So what is made public? That's the key point. Any other thoughts? Yes? Why? No, why? Can anyone spend what he doesn't have?
No, because it's a blockchain, so we don't have any proof that the block existed before. There's still the whole ledger, which I prove for the transaction.
So my question here, can anyone spend what he or she doesn't have? That's your question, right? Is this yes or no? If your answer is yes, why? No, why? That's my question. Anyone? This is a simple question, right? Yeah, Alice.
No, because there's no chain before the
No, and Because
It doesn't have any proof of existence before. Like
proof of existence of what before?
the ledger.
Our ledger. Ledger is the whole record of transactions made in the past, right? So what existence of what? Bitcoin? More precise? More specific, please? Existence of what? You have to prove something that has existed before in order for you to be able to spend it, right? What is that thing that you are? Existence of what? Yep.
If you're trying to spend 10,000 Bitcoin, you should have proof where the 10,000 Bitcoin came from.
Yeah. That means I need to be able to show I have this much Bitcoin given to me by somebody else in the past, right? Then because this has been made public, I should be able to show that, right? Where in the ledger I have this transaction. But what did I say? Blockchain is a ledger left open in public. Anybody can see it. Anybody can see the owner of the private key of this address or public key has this much Bitcoin. Anybody can see it by themselves. So in cryptography, the trust is built because you are able to verify by yourself. I can see it by myself. I can see, open up, and then find this transaction. We call this hash of this transaction as transaction ID and such block. There is my Bitcoin. I can spend this Bitcoin because I have private key. Right? If I don't have a private key, even though I know that it was given to me, I cannot spend. Okay? Make sense? Okay. So the answer: can anyone spend what he or she doesn't have? No, right? Because it is made public in the past. So that actually tells you what the validator of the network or the miner of the network has to do. What does the miner has to do? A miner. A miner is who is spending electric energy to build the next block using proof of work system, right? Who does proof of work? What does the miner has to verify? Miner has to verify if someone wants to spend like this transaction. This has been recorded in the blockchain, and then somebody made this transaction and send out to the internet. Then miner has to verify, right? If this has a signature in it, right? And then basically that's it. Okay, and then B has enough fund in the record. Okay, then that's what verifier has to do. Right? Proof of work miner has to do. Okay, so those are the mechanism of blockchain, and this is revolutionizing the world. Not only the AI is revolutionizing, but this also. You can imagine, world global currency has been born, right? And during this economic and financial crisis caused by the bank collapses in America, Bitcoin prices goes up, right? Because there is a financial problems, right? And all right, so